We have our theme for this year, under construction, and apparently people have constructed things out of these building blocks here, but what if you actually need to take these apart again and understand how they were put together in the first place? That is the study of reverse engineering. And for the reverse engineering of integrated circuits specifically, we have Ulf Wetzger here to give us a quick rundown, a beginner's guide. And apparently we might be alive at the end of this session. Welcome.
Yeah. So first things first, yesterday we had a great workshop, but it started super chaotic, and the same is with this talk. I finished the slides like 1.5 hours ago, and I didn't have a real test run, so I have the feeling that I will be short on time, so let's start. First disclaimer, I'm totally not a professional. I'm not related to any IC design or failure analysis of ICs. This is a project out of pure curiosity. And I did all this stuff with the help of the silicon-prone community, which are incredible folks that answered all my questions and gave me great ideas on how to proceed. I also have to thank my wife, because she explained me all the stuff about microscopy, optics, and image analysis, and also all my friends, which kept me running with these nerdy projects, because they are nerds themselves. Second disclaimer, and this is a really important one. Some of the chemicals and techniques that I'm going to talk about are incredibly dangerous. They are super toxic, and some of them will even kill you if you handle them in a false way. So definitely read and follow all the safety protocols. And you might also want to talk to your neighbors and tell them a little bit about your strange hobbies, because otherwise you will run in quite awkward situations. So let's start. I think every one of you has seen some CPU or some microchip, and typically you know them as these black bug-like devices with some leads on the side. And this black stuff is typically epoxy with some compound to give it a bit more strength. It's typically fiberglass. And if you remove this molding compound, then you will see the lead frame. This is actually, when they produce it, you have like a long band or a long stripe of these lead frames. And in the middle, they will glue the die. The die is the actually silicon chip itself. And it has some pads on the sides, typically. And then you will have small bond wires which interconnect the chip between the legs on the outside. The chip itself, so the die, is on a layered structure. So you have like, this is a super simplified image on the right side. So it has like this substrate layer. It's typically N or P substrate. Inside it, you will find the PMOS and NMOS transistors, or bipolar transistors, depending on what you're looking at. They are built of doped layer, so it's the so-called diffusion layer, and on top of it you have the polysilicon, and these form the transistor itself. On top of it you have multiple metal layers. It's like on a PCB. They interconnect all these transistors and components which you find on the die. So it's not only transistors, you also have some resistors and some capacitors and so on. And typically in the old chips you will have only a few number of metal layers. For a beginner it's always nice to have only one metal layer. But it can go up to, I think, 15 or something like this, and then will get quite messy. As I said before, on top you will have the pads, where you have to interconnect with the bond wires to the leads of the package. This is not only the only package type that exists. So here you can see one SMD package, and next to it there's a so-called chip-on-board package. Here you don't have the lead frame. They simply take the die, they glue it on the PCB and bond it directly on the PCB. And then you will have like this epoxy blob on top of it, so it's protected against environmental influences. Then there are ceramic packages. They were used, if anyone is doing retro computing, you will find them quite often because they were used in the past quite often. Nowadays, they are only used for special purposes and prototyping. For transistors and op-amps, also especially in the past, you could find these metal packages, canned packages. They get quite big for certain RF devices, but they are not that common also nowadays. Only for high power devices you can find them. But still, we have to deal with these package types. This is not complete, but these are the most common ones. And now we want to see the die, actually. So we somehow have to open these packages. And one method is the mechanical opening them. For a ceramic package, you can just take a flat screwdriver or a chisel, hit it with, or you put it in a vise, then you hit it with a hammer, and suddenly the lid pops up because there is a low melting glass adhesive between the two pieces of the ceramic package. Other ceramic packages, they have like a metal lid which is soldered on. You can open them by prying them open with a utility knife. Sometimes you have to saw a small cut inside one of the edges so that you get under the metal lid and then you open it. And then you have this huge, in this case it's a quite huge RF modulator, which you simply can saw open, but you can also saw open these small packages. There are also other techniques for opening them, but these are the most beginner-friendly, but they come with a risk, because you will have some small leftovers from sawing, so sawdust and so on, which might fly on the top of your die, and this is not good for optical inspection, and you have to clean it, but when you clean it, you typically break the bond wires. So most of these methods, they have also a downside, even if they are super simple to perform. The next method, which is also quite common and often used, is like softening the epoxy compound. This can be done with hot air. So you just heat it up. You can put your IC inside a vise and heat it with a heat gun, and then opening with needle nose pliers, or which Silicon Insider is commonly doing, because he's like real pro on this. He opened more than 8,000 ICs and mostly using this method. He uses two pliers, one quite beefy one to hold the IC, and then he opens it with a second pair of pliers. Typically, you heat it up, and then you wiggle around, and then you see that it starts moving, gets some cracks, and then it opens. This technique is also super helpful when removing these CUB blobs, because there is less reinforcement inside this epoxy compound. So you can heat it up, and then you take a utility knife, and then it's quite easy to lift some flakes of the epoxy. Sometimes you will break the IC. In the beginning, you break them quite often because you use too much force. So you need to get used to this process. But quite commonly, you have some leftovers of epoxy on top of the die that you need to remove with another method. Then there are like high temperature methods. We can use a blowtorch, or Richie is doing it. He built himself a furnace for this, for heating it up, and basically you burn all the organic compounds, and left over is just some carbon residue that you can just break super easily because it's very brittle. You can use a blowtorch for this. With the blowtorch method, I also was able to open ceramic packages because you heat them up over 400 degrees, and basically the glass sealing adhesive is just melting away, and if you have it in a vise, you just pop off the ceramic lid. If you want to remove some polyamide layers, I don't go in this deeply in this talk, but sometimes you have a polyamide layer on top of it. You can burn it off, but every time you put the flame inside the top of the die, it's a high risk of damaging the glass on top of it because it will simply melt, and then you will have problems imaging it. So try to avoid it, and therefore there's this heatsink method where you can spread the heat a bit more evenly so that it is not breaking. Now there comes the more dangerous part. Some of these methods are not really applicable to Europeans because in Europe you don't get acids in this high concentrations easily, at least not as a private person. So one method is to use sulfuric acid. You place it inside the glass container, you heat it up for at about 200 degrees Celsius. You boil it for some time. It's, as you can see on the picture from Septobars, it's like really spilling around, and he even placed baking soda around it so that the spills directly get neutralized when they drop out of the metal container. But it's also possible, so he dissolves the whole chip and the leftovers just the dye. But it's also possible to use it to make something called live chips decapture. So you just make a small hole inside the top of the chip, but not too deep. You make a drop of sulfuric acid on it, you heat it up, and you have to repeat this until you reach the dye. If you are lucky, then the bond wires are still intact and you can run the chip as you did before. Therefore, also fuming nitric acid, which is also super nasty stuff, can be used. And when you have this live decaps where the chip is still alive, you can do quite some fun stuff with it. On the right, you see two different possibilities to use it from John. One is with a heat gun, so he heats up this canister, and the thing beneath it's like spinning, so it's mixing all the time. There he dissolves the chip completely, and the dye is left over. And in front you have a typical heat plate with also this where you can place the chip on top, and you make this live decaps like on the left side. This method is actually the one that I use quite commonly because the materials are easy to get. It's basically, I think it's called rosin, but I always say resin, I don't know why. So it's colophonium. It's easy to get because you can get it from eBay in huge packages of 1 kilogram. It's used for treating the surface of furniture and restoration purposes. And what you need to do is you need to boil it up, the whole chip inside the colophony at about 300 degrees for about 20 minutes. And suddenly, or most of the time, it's completely dissolved. This also with the other methods, this depends on the epoxy because the epoxy is not always the same. Some epoxy is harder, and then there's also these glass faser stuff inside, which makes it sometimes a bit complicated. What I'm doing is I use the method in the middle most. It's like a soldering pot filled with sand. Then there is this beaker inside, which is actually a whiskey bottle where I sort off the top. And I place this thing, which is shown on the right, inside. And these are for people that smoke pipes. This is a pipe filter. And the funny thing is that you can place 2 or more dyes in it, and they are still separated after the decapping, so you know which one is which. This is quite important because it's very confusing if you need to find out later on. You definitely need to clean them with acetone afterwards because the resin is stuck on all over the dye. It's not that nasty, but still I wear a respiratory mask for this because it's not. It's like when you do soldering, the smoke is actually the same, but here you get in 1 minute the thing that you breathe in for a whole lifespan, I would say. Then there is some people are playing with lasers. So this is a fiber laser on the left side, and they go down, they burn basically the epoxy. But when you see the middle picture, typically the heat of the laser destroys the surface of the dye. So what people tend to do is they stop like a small bit before they reach the dye. So they have to test it out before on another chip. And the rest they dissolve with acids, but in this case you only need 1 drop of acid. If you want to observe the backside of the die, it's a totally different thing. This is what you can see on the right, because you can go down to the lead frame, all with the laser, and then you pop off the middle part, the lead frame, and you directly see the button side of the die. And this can be used for laser attacks in fault injection. So what do you do with the die? At first, you somehow have to take a bit care of your die, because you need to glue it on. Typically, I use a cover slide, a microscope slide, or a cover glass for microscopy, and you need to glue it on top of it. But here you already have to be careful, because when you use super glue and then later on you clean it with acetone, you might remove the chip again. So what can be done is to use standard glue stick. You take a piece of the glue, you spread it with a toothpick, and then you glue the die to the microscope slide, and later on you can simply dissolve it in water, so you get the chip off again. The funny thing is that it's resistant to acetone. The second technique that is quite nice is to use standard beeswax. You heat up a small piece of wax up to 66 degrees, then it spreads evenly, and you place the die on top of it. If you want to remove it later on, you can use white spirit for this. What I started to do is I use this small label printer. I make a photo of the chip and directly print out the image of the markings on the chip, and I glue it on the back of the cover glass. For cleaning, you can use Q-tips, but since they are out of cotton and you still have, or most of the time you will still have leftovers from the bond wires, it will get quite linty. So these foam swaps are better to use in the end for cleaning it off with acetone before you imaging it. So in theory, we can now image the chip, but sometimes you don't only want to look at the metal layer. So we might need to delayer the chip. So remove the metal layer to see the poly and diffusion beneath. One technique that can be used is lapping. There are actually professional lapping machines which cost quite some money. But if you want to do it at home, you can do the same stuff as Ken did when he reverse engineered the famous Pentium bug. It was all over the internet when he did this. And he simply used the eraser part of a pencil and put a small piece of 150 sandpaper on top of it, and then he carefully sanded away the metal layer. What I did is a method that I learned from Ork, from Emu Russia. He used some polishing compound. I used diamond paste, which is used for sharpening knives. I used like 5-micron diamond paste for this. And you just take a Dremel and this polishing disc, and then you carefully remove the upper layers. I also built this thing on the right side to get a bit more control. So this is just a piece of granite that I got from the hardware store. There's a nylon sticker, which is used for repairing tents on top of it. And then I use the same diamond paste and polish it down. It's a real pain because I use a washer to keep it more even when polishing it, and it takes forever that you reduce the size of the washer. So the quickest method is the one with the Dremel, and it works quite okay. Delayering with wet etching. This is really nasty because you need to use hydrofluoric acid. This stuff scares me to death every time because when you get it on your hand, it's not like damaging your skin. It's going to your bones, into your body, and then it's in your body, and basically you have quite a big problem. Also, the fumes which are created when it dissolves glass are highly toxic, also in small amounts. So definitely you need to use a fume hood for this. But the fun thing is It's used in this armor etch stuff. This is this bottle which you see in the middle. It's you can get it from these hobby stores to etch glass at home. And it says, okay, you have to wear some gloves and that's it. I got it from eBay from Turkey, and I'm 100% sure that this is not good to do this at home for etching glass. The other thing that I have is from the dental supplies. It's used for etching ceramics, and this stuff is the best that I got, because in this armor etch cream, there are also other components inside, and this makes the etching process quite uncontrollable. In the US, you go to the hardware store and you can simply buy a rust remover, which uses hydrofluoric acid, which is super scary for me. But all the guys in the US, they use it. They are careful because they know what they're dealing with. But I think if someone gets it from the hardware store, yeah. The procedure is you put not even a drop. It's like a super small amount on top of your die. Then it will start to dissolve the silicium dioxide, so it's glass top layer. And if you want to time it, then you wait some seconds, you clean it off, you look if it's already through the glass layer under a microscope, and you repeat it until you reach the metal layer. A technique that I learned from InfoSec DJ is he's actually doing it under a microscope, and as soon as bubbles appear, he knows that he hits metal. So just wait until it starts to bubble like this, and then you need to directly clean it off so that you can remove the metal layer. The metal layer is just, what is Salzsäure? It's written there. You need to etch away the metal compound or the metal layer by just like etching it away with this mixture. It works actually quite well. Here's a small comparison from a test that I did actually 2 days ago. You have an unprocessed die. It's from a French telephone card. Where you see all the metal layers, then there's the lapping. You can directly see that all the corners are rounded off, so you don't see structures which are at the outer side of the die. And here I was a bit too aggressive because you can see that I also removed the poly layer and only diffusion is left over, and you can maybe guess at some points where the diffusion was. On the right side, there's the wet etch that I did, and here you can see basically everything. So metal is removed, and you can see diffusion and poly, which is nice for imaging and reverse engineering. So now we want to image. We have like a delayer chip, or we have the decap chip. And at first you have to get a microscope. The standard microscope that you might all know is the transmitted light microscopy technique. It's the biological microscopes. So you have light which comes from beneath. It shines through the sample into the objective, and then it comes out of the eyepiece. This is a problem because for visible light cannot transmit through the chip itself. And therefore you need to use reflected light microscopy, where the light source is on top. There's a half mirror which reflects the light downwards to the sample. It reflects back, and then it comes out of the eyepiece so that you can see it. If you just want to get started and you have a biological microscope, this is how I started. You can start to modify the biological microscope by just shining a light in one of the eyepieces. This is super shitty because you get a lot of reflections and the image is quite bad, but you can see something, and it's really cool when the first time you see some dye. But if you need to buy a new one, definitely go for reflected light microscopy microscopes. The most important thing is the objective itself. So there are these labels, and in the beginning I had no clue what they all mean. I only noticed that the magnification is written there, and magnification is quite simple. So it's the factor which the image gets bigger. And when you, in this case, it's 10 times, and typically the eyepieces also have 10 times. So in the microscope with a 10 times objective, you get 100 times magnification. But then it's like M-plan objective. This is used for metallogic microscopes, so where the light comes from top. And plan means that the image is corrected so that all the image is actually projecting one layer, and this is important when you want to stitch images. Then you have this tube length. This tube length is important when you buy an objective because you need to take care that this fits your microscope. The tube length is actually the distance the light travels from the objective to the eyepiece, and this actually doesn't change in your microscope. So if it's like a 160, you need to buy 160 objectives. There is also infinity length corrected objectives, and personally mine is a bit strange. It has or not strange, it's uncommon, it's 210. Yeah. Then you have these color markings. I don't go into this deeply, but immersion microscopy is a thing to create better or to improve the image quality. But talk to me later, or you have to look it up. The first thing that at least I was not aware of is what the numerical aperture is. And now we have to go a bit into optics, because this is related to the optical resolution and is super important when you image your dyes. So this was found out by Ernst Abbe, and he noticed that the opening angle, so half the opening angle, is somehow related to the optical resolution. So the numerical aperture is actually this formula on top. So you have the refraction index of the medium between your objective and your sample. Could be glass, air, oil, or water. And the higher the numerical aperture is, the wider the angle is. And this means that you get more light which comes into your objective. And why is this important? When you want to differentiate 2 points on the microscope, so this is the optical resolution. This can be represented by these 2 slits inside this surface. You get interference patterns. And if you want to distinguish these 2 slits inside this surface, you have to at least see the first maxima of the interference pattern. And the closer these slits are, the wider the interference pattern gets. So the problem is when you want to distinguish 2 small objects, the opening angle of your objective has to be super wide. So takeaway message is higher numerical aperture is better for optical resolution, but it's incredibly expensive if you want to buy these objectives. They can go up to thousands of euros, even used. So what should you buy when you want to start doing this? I asked around, and the guys and girls, they sent me pictures of their microscopes, and quite common are these Olympus microscopes and Amscope. I personally have a Nikon, and I got it from eBay quite cheaply. So if you buy a cheaper microscope, it's definitely not automated. So it's for manually moving around the XY plane and also the Z stage. So all the people which have these more cheaper microscopes, they somehow automate it with some motors that you can see on some of these images. When you buy one over eBay, you definitely have to check for mold and scratches on the objective, because this is basically the most expensive part of your microscope. So ask the seller if they can send you a picture where light shines through the objective so that you can see if it's super dirty or even broken. But still, there's a high risk that it's not good. There are 3D printed microscopes, Puma and OpenFlexure. It's super cool for learning all these optics stuff, and you can do imaging with it, also with this reflective illumination. But certainly you will not get the quality like these more professional scopes, I would say, without tuning a lot. Then you want to have a camera. The rule of thumb is if you have like a 1-inch sensor, which is quite expensive, you should go for a resolution more than 20 megapixels. If you go for a half-inch sensor, which reduces the size that you get from imaging, so you have to take more pictures to stitch in the end, you should go for more than 5 megapixels. This is super rough. It's super complicated to buy microscopes, but so now let's start with reverse engineering. So the first things that you can do, and it's quite easy, is to identify chips. Why do you need this? I don't know, when you open some devices, especially from China, they somehow laser away the markings on the chip, so you don't know what it is. And if you have this chip on board things, you always never know what it is, which is inside this package. So you basically open it, you make an image, and for the thing that I did on top is this super cheap handheld game console for €6. I found out that there's a marking. I looked at the internet, and there's actually a company in Taiwan. They only produce so-called NES on a chip, so it's basically NES clones. This is what they do. I found a tool chain and some data sheets, and I was able to build a flash reader and writer so that I can tinker around with this device. Another fun thing is I saw these unlock SIM cards. It's quite strange because you place it on the SIM card and then you put both devices inside your mobile phone, and it somehow seems to help you to unlock the phone. I never tested it, but for me it sounded like man in the middle for smart cards, and this is super interesting. So I looked at the chip, and it's actually, I think it was a Cortex M0 microcontroller, and you could even program it with serial wire debug, so you have like a programmable man-in-the-middle device for smart cards. The next thing that you typically do is you try to identify certain patterns and features on the chip. If you have some experience, you can quite quickly see, or I think even without experience, you quite quickly see what memory is, because it's a really homogeneous structure. But if you have more experience, you can differentiate between different memory types. You can see shift registers, you can see registers in general. If you have RF components like Bluetooth and Wi-Fi, you see super funky structures with coils and so on the chip. And one super interesting for me was that Andrew Zonberg told me that he uses this also for chips which are produced with a resolution that you cannot capture with classical optical microscopy. So if you have like, this is the Raspberry Pi Pico 2, so the RP2350, I think it's produced in 40 nanometers, so you will have no chance with a standard microscope to see anything, because it's under the resolution, under the wavelength of light, of visible light. And he still said that when you image it, you get interference patterns because of some quite homogeneous structures. The colors that you see on the chip are created because of the pattern of the transistors and the metal layers. And therefore you can identify what are similar structures. Here you can clearly see memory, and if you check on the data sheet, then you can guess, depending on the size of the memory, so how many kilobytes it is, you can guess which area it's which, and you identify over the chip where the CPU or the main part of the CPU is, where's memory and all the peripherals and all this stuff. And they use it for more advanced attacks where they used electron microscopy or forced ion beam as a step before, so that they identify where they should start imaging with these more time-consuming techniques. Now we go down to reverse engineering transistors. In this example, this is an NMOS standard cell. On the top left, you can see the two metal stripes. These are the VDD and VCC, so it's power and ground. Then in green, I colored the poly layer, and the diffusion layer is in red. As soon as diffusion and poly overlaps, this creates a transistor. And therefore, you can start painting small transistor imagings on top of these colored areas of your chip. And if you trace the interconnects, you suddenly find out how everything is connected. For a NMOS type of process, there is something, so you only have NMOS transistors over the whole chip, and therefore you need so-called enhancement and depletion, enhancement or depletion type transistors, which actually form a resistor. So the transistor on top is actually working as a resistor. If you trace this, you can then come up which the logic functions are. If you push this even further, like Unilink did it, he traced the whole chip. He did all the interconnects. He even wrote his own software for reverse engineering the chip and simulating it. So it's really impressive. You can do the same for CMOS processes. Here, there's the difference that for all NMOS processors, you have the complementary PMOS processor. This is depending on the fusion layer, how it's doped, and you basically do the same thing. You always look for areas where where poly is over diffusion. This is a transistor. Then you trace back all the interconnects, and you come up with the transistor connection, and therefore with the logical function. Also here, it's Andreas Singer did a really crazy thing. He reverse engineered the whole first Game Boy GPU. You have like with Google Maps, you have like a map where you can zoom in and see all these standard cells inside the whole chip and how they are interconnected. It's really crazy. Then there's one thing which is quite easy to reverse engineer. These are so-called gate arrays. A gate array is a complete homogeneous structure of these so-called basic cells. The basic cell is just an NMOS and a PMOS structure without metal interconnects. And when the designer wants to give it some logic function, he just needs to place the metal interconnects based on some library function. So they can produce the chip without the metal layer, and then you can put the metal layer on top of it to give it some kind of a function. And the fun thing is you only need to trace the metal interconnects. And since this is also a library-based design, you find once a NAND chip, and then you can search for it all over the chip in this homogeneous structure, and you only need to trace the interconnects between these logic blocks. Eric did this in KiCad, so in a PCB layout program. So he created like a footprint for all these standard blocks, and then he placed the traces in between to reverse engineer the whole chip. Then there are mask ROMs. Mask ROMs are basically memory pieces of memory that are they're not even one-time programmed. They are programmed in the factory by defining the mask of the chip. When you read them out, they will never be changed, and this is quite a problem when you find a bug inside the code which is written there. And as you can see on the top left, you have these dark and these light dots. When you look at if you zoom in and you have a close-up, then you can see that these are all basically transistors, and depending on if there is a wire or not connected, these transistors are connected to the bit line or they are not connected to the bit line. So when you read out the wires, you read out the bits, because a 1 is actually a transistor which is not connected. Then one thing that InfoSec DJ told me about like 1 week ago, I decapped a 268. This is actually my first computer that I owned, and he told me that during this time they used quite a lot of programmable array logic, so PLAs inside these chips to represent logic functions. This is also, again, a quite homogeneous structure. You have like on the left side, you have, in this case, on the lower side, I think. I wrote it. So you have an AND plane and an OR plane, and depending on the interconnection between this defines the logic function of the chip. Here you can also see the wires, but if you go down to the diffusion layer, you can clearly see that sometimes there is a transistor and sometimes there's no transistor. This is actually like a NOR gate, and this defines the logic function of the chip. Final slide. Another fun thing that Libby told me about is, or that she played around with it quite a lot. If you have a transistor and the transistor switches, it emits a really weak infrared signal. And if you do this quite often and you have a long time exposure, you can see which transistors flip inside the chip. So if you really write or if you spam a certain register inside a chip and you make an image with a long time exposure for 30 seconds, they start to light up when you have like an infrared sensor on top of it. And basically infrared sensors are just standard cameras with an IR filter removed. Theoretically, you need special objectives for this, and you need also quite good cameras for this, but for this purpose, you can use standard objectives and also like a modified, or I think that you can even buy Raspberry Pi cameras without IR filter. And the fun thing is that you don't need to reverse engineer the whole chip to identify which area you are interested most in. And later on, you can start attacking this with some fault injection or whatever you want to do. So this is my last slide. I'm super happy that I made it on time. Thank you very much.
Thank you, Ulf. We have 4 minutes for questions. Yes, there's one.
Hey, great, beautiful, super important talk to our community here. Thanks, Ulf.
Thank you, Stefan.
I have a non-serious question and a serious one. Let's start with the non-serious. I'm really curious what you have for fun with your neighbors when you carry out in and out your whole set of assets. So tell me later, but not now. My serious question is, you said in the very first beginning to get the chip out of your device, whatever you hit it maybe with a hammer or whatever. I do not want to do. I have a use case where there is some ugly, nasty diamond film material soldered underneath the chip where it's soldered with a ball grid area. And I want to get rid out of the chip. It's a mobile application. I think everybody has a water accident maybe and want to get out of the memory chip. So 2 components. It's not only soldered, it's also diamond film material underneath. How do you get rid of the chip without destroying it?
So with these kinds of chips, there are actually 2 problems that I noticed. One is that if you have a BGA, typically they have like a standard PCB at the bottom layer sometimes. And when you want to dissolve it, it's also epoxy with fiberglass. It's really nasty. And especially if you want to do it with hot air, then you have the problem that you have like this small PCB piece in the chip. And it's quite bad to get the epoxy off correctly. And the second thing is there is some, how is it called? If you have like a flip chip device, then you have, is it called filler? There's some kind of glue between the chip so that it's not moving. And basically you have to burn it off. I had like a Spark CPU and I had to take this blowtorch and I broke the first one because it just got a crack because of all the heat differences inside the chip, so it was quite complicated.
When you like remove all the layers and reverse engineer the whole thing and like along the way killed your neighbors, and what are the use cases of like the reversed engineered IC?
This is now the point where I'm not a professional. I don't care. This is pure curiosity for me. I want to know more about all these techniques. I fiddled around with decapping only for the fun of to find or to improve the process. And my driver was that since I'm young, I'm interested in like telephone cards. This is how I started with all this hacking stuff, and I have like 1,000 telephone cards at home, and I was wondering how they work and so on. And we had like a great talk yesterday that everyone could see from Mitzi, and we talked a lot. And I took the approach to take a look at the die and to try to find out how the telephone cards internally work, because basically there's only high-level documentation for this. But it's pure fun, nothing else.
Great. Thank you, Ulf.
Thanks.